All right, hi everybody. This is question 90 from chapter 2. It's the last one in chapter 2. In this question, we have a contamination of some natural iodine, for which we're given the atomic mass, with a sample of radioactive iodine, which we're given the mass. We're given the mass of the amount of the contaminant, and we're also given the molar mass of the iodine, and we're asked to find the apparent atomic mass of the entire contaminated sample. So we did a similar question to this earlier with nitrogen, in which case we were looking for essentially the mole fraction for the N14 and N15 isotopes, and in this case it's kind of backwards. So we don't have the formula weight of, we'll just call this, that's supposed to be a C. We'll call this contaminated iodine, like that. We don't have this value. So we need this amount of the first, we'll just do this of normal iodine. I have 12.3849 grams. And, whoops, hang on, sorry. I knew I was screwing something up there. Okay, we're gonna write our atomic mass here. This is 126. This is of normal iodine, 9045. Yeah, grams per mole. Perfect. That is much better. Okay, and then we get some amount of the contaminated iodine, 129, which is 128.9050 U. That there is a 5. Okay, so we're looking for X and Y in this case, but we are given information enough to solve it, and our end goal is this value here. So what we're going to do is we're going to take the masses that we're given of both of these, and we're going to calculate it. We're going to calculate a mole fraction with it. So let's find first the moles of. Oops, sorry. Goodness. Okay, let's find the moles of normal iodine first. So that's iodine. Yeah, we'll just leave it like that. Okay, this was 12.3849. Right? We want moles of both these things. We're just dividing mass by the formula weights that we had. 9045 grams per mole. That gives us a total here of 0.097. I'm going to keep a large amount of figures here. Okay, for the radioactive iodine that's contaminating it, that's 129. We had, fortunately, many fewer grams, divided by 128.9050. Okay, and this gives us a much smaller figure. 7.76308 times 10 to the negative 3 moles. Okay, so we need a mole fraction. We've only got 2 components, so I can divide either of these by the total. That is, these 2 values summed together, and then the other one is gonna be the difference between that and 1. That's to say, like up here, I can write y is equal to 1 minus x. Right, which is exactly what we're going to do. That's what we did for nitrogen too. So let's get ourselves a mole fraction of the normal iodine. Okay, so this is where was it? So 9.75922 times 10 to the negative 2. That is over this plus this. 75922 times 10 to the negative 2 plus 7.76308 times 10 to the negative 3. That gives a total of 0.926315. So that is going to be our X value. We're going to stick that up here. X equals 0.926315, right? Yeah, we did write X in front of that one, so this is going to work out. Okay, I'm just going to make some space. Okay. All right, so to find this value, we plug this thing in and this thing in for this, and we solve these things exactly like we did in the nitrogen question. So we're going to have 1269045, right, in grams per mole times X value, which is 315, plus, sorry, even I can do better than that one. Okay, 128.9050 times 1 minus this value, 926,315. Okay, multiply, it's like do this, obviously this difference between you multiply this, but when you crunch all those numbers, you are going to get 127.0519. Right, and that is the formula. That's the formula weight of your contaminated sample of iodine.